Hi, today we'll talk about nested quantifiers and contraposition. So to explain the idea, I'll just start with an example. Check if the following statements are true on the domain of integers. We call it Z. Statement number 1. For every x, there exists y such that x plus y equals to 0. And the second one looks very similar, but just we'll switch the order of quantifiers. So there exists y such that for every x, x plus y equals 0. In these two examples, we have the form of a predicate formula, or the pattern, where we actually observe the nested quantifiers. So what is that all about? Let's look at the inside formula. So inside formula on its own has a quantifier. And then the outside formula that acts on that inside formula also has quantifier. So when we have quantifier acting on a formula that also starts with a quantifier, we call this nested quantifiers. The same situation happens here, although now exists y is outside quantifier acting on a formula that has a universal quantifier. So let's see, how do we decide if such a formula is true or false, and also how will that switch between the quantifiers influence our decision about considering it to be true or false. So let me consider the first statement. So no matter what's in the green box, if you see for every x statement, that means we should substitute all the elements from the domain integers and then check if the statement obtained is valid. So we'll get the following. There exists y such that 0 plus y is 0. That's when x is 0. If I plug in x equals 1, I want there exists y such that 1 plus y is 0. When x is 2, there exists y such that 2 plus y is 0, and so on. For x equals negative 1, exists y such that negative 1 plus y is 0, and so on. So my question is, do we think that all these statements are true? If we can confirm that, then we can say that our statement L1 is true. Or the other way around, if we find one of them not to be true, then we'll say that universal statement is false, as we've seen in section 1. So let's see. Is there an integer y such that 0 plus y is 0? The answer is yes. And the witness is y equals 0. What about second one? The answer is also yes. The witness is y equals negative 1. This one, again, yes. The witness is y equals negative 2, and so on and so on. You see that it works actually for every integer. In this line, it would be yes. Our witness is y equals 1. So generally, when we observe all these statements together, each of them is true because we were able to find the witness. So since each of them is true, universal statement is true. But let's analyze what happened here. The witnesses that we found, and here they are, they keep changing. So whenever we change x, then we can also change the witness, and that's absolutely legitimate argumentation, because here we were supposed for every x to find a witness, and there is no reason to expect that witness to stay the same all the time. Let me do it side by side now for the statement number 2. We have nested quantifiers again, but now existential quantifier comes first. So what will happen if I wanted this to be true? I need to find the witness up front. So try to find a witness C such that for every x, x plus c equals 0. And then, I don't know, maybe we can find the witness, or maybe it's just not even worth trying to find it. So I'm not going to disclose that witness because I don't have the idea what it should be, but let me see what kind of properties should that witness have. So that witness should serve all the possible x's. So whatever I choose for c, if there is such c, here's what that c has to do. When x equals 1, I need to have that 1 plus c 0. When x is 0, I need to have for the same c that 0 plus c is 0, and so on. And that c should at the same time be -1 and at the same time be 0. There's no c that satisfies both properties, so that's telling us that we cannot find a witness c that would make this statement true, so that such a witness does not exist, and the statement is false. So here we have false, and this one is true. So what is the main thing that makes that made this statement true and this one false? Because here we were allowed, since each x needed its own witness, we were allowed to change the witness. In the second one, we had to come up with a witness first, so generally we were supposed to find a witness that will work simultaneously for all the x's, and such a number does not exist, so that's why this is false. So what did we learn from this problem? I would say 2 things. One, that we saw the example how the nested quantifiers look like. We also saw how to open them in a way to see their validity. So we open quantifiers from outside inside. And what else? We saw how important it is to keep the order of quantifiers properly, because if we switch the quantifiers, then the meaning of the sentence changes, and status of being true or false also might change. So I think that this is a pretty good example to tell us about this important construction about formulas. All right, let's now do a few examples where we want to write formulas involving nested quantifiers to represent some sentences from everyday English or from mathematics expressed in everyday language, and then also the other way around. So here is the example 222. We want to express in everyday English for every x in R, there exists a y in R such that x plus y equals 0. So when you need to translate to ordinary language mathematical sentences, then I would suggest first not to be too ambitious, meaning to do it step by step. So what I would do here, I would just box this inside formula and then try to express the fact that outside of that formula we have universal quantifiers. So I would say for every real number x, and then box. So don't rush it, just first say properly what's written in the outside quantifier. And now we want to open what's in the box. So in the box it says there exists y from R, so there exists a real number x. I need a little bigger box. So, such that, I'm sorry, the other real number y, such that x plus y equals to 0. This is still quite mathematical sentence, just instead of writing, we are saying for every and there exists. And then what? Now we can relax this a little bit more to have a sentence that looks a little more natural and less mathematical, and we can say the following, especially if we invent some terminology. So when this happens, we say that y is opposite of x. And then what? We can say now, in a little bit more natural sentence, for every real number x, there exists its opposite real number. So here we don't have any formulas, everything is a sentence, or we can just say, diverging a little more from the original sentence and say every real number has its opposite. And then real number, or if it's clear from the context, sometimes we just make a shorter sentence. So when you translate something from, and when you are trying to understand actually what is written in the formula, then good thing is just to break the sentence into its subformulas and then interpret basically from outside inside, then make maybe shortcuts, and then things are much easier to translate. All right, let's also practice the other direction. If you have informal argument and we are not sure how to understand it, how to make formal argument out of it. So here is the example 224. There is a largest positive integer. Okay. So how would we write this, the appropriate mathematical sentence that will help us to understand this and check validity of this statement more carefully? Again, the main thing here is that there is something. So there is something, there is an object. Okay. So what do we do here? That largest positive integer, we'll give it a name. Since it's undisclosed and not fixed, then we'll call it x. Okay? And then if that object exists, we'll say there exists x. So here's the way to start this. There exists x such that x is a largest positive integer. So don't rush into formulas. Keep the structure of your sentence and then build mathematical statement slowly. And then what? So x is the largest positive integer. First, it is a positive integer. So maybe we can say that within parentheses, or sometimes we adjust the quantifier and say the following: there exists x from z plus. So that means x is a positive integer. And then again, x is the largest positive integer. And now we need to express somehow, and we also learn those kind of patterns, like in language you learn block of few sentences or some expression used in certain situations. So generally being the largest means being larger than everybody else. So that means for every x, there exists x in z plus such that for every other y from z plus, so if someone offers another candidate, we'll beat that candidate. So for every y from z plus, we'll have what? That y is less than or equal x. Here it is. And then, of course, these parentheses are not necessary very often. We just assume the order, so you don't need to protect it with parentheses. So we say what? There exists a positive integer such that every other positive integer is dominated by our integer x, and that's exactly what means to be the largest positive integer. And then what? You can say, all right, can we test if this statement is true? So again, let's check it. So is it true? Let's test it. Suppose someone can really come up with a witness for this. Let's see, be a witness. So we would have then for that C, that for every y from z plus, y would be less than or equal c. But then what? If it's true for every y, it is true, must be true for y equals c plus 1. So then we would have c plus 1 less or equal c, then we add negative c to both sides, and we get 1 less or equal 0, which is a contradiction. So generally it cannot be that anyone can come up with a witness. There are no witnesses, so this statement is false. So I hope that these few examples are helping us to understand that process of step-by-step translating everyday life language or just standard mathematical language into the formal language and vice versa. And then let me just mention at the end something about contraposition. So contraposition of a statement is done only on its propositional part. So let me put a subtitle, contraposition. So you remember from propositional calculus, if we have P implies Q, that's equivalent. How do we do contraposition? We take negations and we reverse them. So not Q implies not P, and this is very useful in all kinds of arguments provided in mathematics. So those are equivalent statements. That means proving one has the same value or same difficulty as proving the other one. So what happens? Can we do contraposition in the predicate calculus? Here is the example. For every x from R, x times x plus 1 greater than 0 implies x greater than 0 or x less than negative 1. So what happened here? We have quantifiers outside. So if I were to hide the quantifiers, what we have inside has a pure propositional structure, and it looks really like P implies Q, where P and Q are kind of zoomed in, and then we saw the structure of those. So what would the contraposition be? Contraposition is done only to the propositional part, so don't try to go with negation to quantifiers or anything like that. Just copy the quantifier the way it is, and then reverse only the propositional part inside the same way as we did it before. So take negation of the consequence implies negation of the antecedents. So we get all together now the Morgan negation of disjunction, negation goes to each of them individually, negation of x greater than 0, and the negation of x less than -1 implies negation x times x plus 1 greater than 0. And then of course, if we know a little bit our inequality not being greater than 0, that means that x is less than or equal 0, and x is greater or equal to -1 implies negative x plus 1 greater than 0. And what else? Maybe we can say this, but that's really a little stretch. Yes, it's nicer if we write it like we usually do in algebra courses, if x is between -1 and 0, although this is not really maybe completely valid statement, but if we have convention that this means this, then we say not true that x plus 1 greater than 0. By the way, the statement about reals true. What it says is actually x times x plus 1 greater, so here is -1, here is 0, so x times x plus 1 is parabola. I mean expression defining parabola, so we are saying if we are between -1 and 0, including the endpoint, our function is not above the ground, which is true, so statement true. So once again, the only thing that's new about contraposition is that it's not done on quantifiers, but just only on propositional